Welcome back uh, to this discussion on these things. So we are talking about the mechanics of wind, or the factors which are influencing or causing to have wind motion. So we have already talked about. So you have pressure differences, Coriolis force, centrifugal force, frictions. So these are some of the influencing factors that causes the motion of the wind to have. So we talked about how pressure gradients impact. So from there, we kind of again talked about the Coriolis force, and we got the correlation of the geostrophic wind velocity with that. Now we can move to look at the uh, some correlation. So what we can look at this effect of pressure gradient and Coriolis force. Okay, so geostrophic wind is kind of a balance of pressure gradient and the Coriolis force. So geostrophic wind is a balance of pressure gradient and the Coriolis force. Now, what we can look at it in a simple case of straight isobars. Let's say we can plot like that. So this is space. This is also space. So this is positive pressure. And this is negative pressure. So what we can have, these are the isobars. So these are all isobars, and you can, so this is where you have wind. This is pressure gradient, and this side is your Coriolis. Okay. So it just like, I mean, other way one can think about, I mean, look at the same thing in kind of an some. So this is R, and where you have VGO. This is your low pressure region. So this is illustration of the gradient with radius of curvature. So in this simple picture, what one you can see that the pressure gradient pushes the wind going upward, and the Coriolis force pushes wind downwards. So the result of that, the wind travels parallel to the isobar. So wind travels parallel to isobars. Okay, because of these two forces which is cancelling each other. That So the result is that wind travels in parallel to isobar, where the acceleration due to pressure gradient and Coriolis effects are balanced. Acceleration which we have 1 by rho by dp dx 2 sine phi omega naught VGO. So this is the acceleration due to Coriolis effect, and this is due to pressure gradient. They balances out. So one thing you can note here that what you can note here is that VGO to pressure gradient, but parallel to isobars. So this is what you get, and for that you can expect to have some kind of an weather map. Obviously, this needs to be complete circle. So this is your low pressure, and this is isobar. So what happens is that, so this is how the in weather map you get to see the low pressure, as we have seen here, low pressure zone and high pressure zone which are uh, getting created. Now we see the centrifugal acceleration. Okay. Geostrophic wind consider the pressure gradient and Coriolis flow. But however, when isobars are curved, which is almost always the case, so that if we draw a situation, let's say this is low pressure zone, this is radius, and then this is incoming wind stream, and this goes like that. So this goes like that. This is BG or omega. So geostrophic wind consider this pressure gradient and the Coriolis force, but the isobars, which are most of the times are curved, there is a third force which affects the wind, is the centrifugal force. So obviously this arises from traveling in a circular path. So anybody is traveling in a circular path, this is the, so this shows the situation where a circular, this is an circular isobar, and wind is traveling along the isobar. Wind is traveling along the isobar. So this is the figure is all about. So the refinement of this VGO is the VG, which is the gradient wind. And that would be at any radius. If something is rotating with an angular velocity, then you can get that. So my acceleration would be Vg square by r, which is omega square r equals to, we can write omega square r square by r. So r here is the radius of curvature of isobar. So Bg is the gradient wind, which is, one can say, the speed of wind along isobar. But one can note that Vg is not equals to Vgo. Okay, but this is still parallel to the isobar. So what we can do now, so hence the calculating in acceleration, which is minus 1 by rho del p by del x. So one extra term is added due to this extra centrifugal force. So there would be 2 sine phi omega naught Vg. So plus Vg square by R. So this is due to Coriolis. This is due to centrifugal. So what we can now write that Vg square plus 2R omega naught sin phi Vg plus minus del p by del x into R by rho 0. So we get Vg equals to minus R omega naught sin phi plus minus R square omega naught square sin square phi minus del p del x by R by rho. So what it here one has to note, Vg is less than Vg. To assess the relevance of centrifugal force, compare co-release, the 2 sine phi omega V0 with, once we compare the co-release, that is co-release is 2 sine phi omega naught Vg and centrifugal, which is Vg square by R. We can compare the ratio between these two. So the ratio is 2 omega naught sine phi Vg Vg square by R. So that gets 2 omega naught sine phi R by Vg. So one can get an estimate between Coriolis and centrifugal, which is going to dominate, and try to find out what is going to be important or not. Okay. So now we are going to look at the effect of friction. So friction, essentially, this depends on surface properties, but generally it slows down the air only in the atmospheric boundary layer. So friction decreases Coriolis and centrifugal forces. So therefore, what happens at a very low altitude, winds tend to move towards the direction of the negative pressure gradient. So that's why at very low altitude, wind tend more towards the direction of negative pressure gradient. But at Earth's surface, if you see, so this is why it goes like that. So this is atmospheric boundary layer. This is because of wind shear. So at Earth's surface, here the wind speed is 0. So wind shear is often described by a logarithmic profile. Wind shear is always defined by a logarithmic profile. So one can say that if this is, let's say, V of E, and at a height Z0, this is, let's say, V naught, and this is direction. Then V naught is speed at altitude Z equals to Z naught. ZR is roughness length. So this is typically order of few millimeter for flat grounds. Then you'll have this V of Z, V naught log of Z by ZR log of Z0 by ZR. So this is the typical logarithmic profile that can be used to calculate the wind shear. I mean, this is something one can think about this friction that's going to. So we would talk. I mean, look at this wind shear and effect of the wind shear when we will be talking about the design aspect of it. So this another parameter which is very important. So we try to see this how this weather maps actually shows the low pressure, high pressure zones and how the wind actually forms. Uh, it's all because of this different altitude and the rotation of the Earth. Okay, so now what we look at is the there are also issues due to issues like you can say that stable and unstable atmospheric stratification. So what happens is that when the sunlight falls on Earth's surface, the surface becomes hot. So also um, a rising piece of air becomes relatively hotter, so it rises. And rising air actually expands and therefore gets cooler. So there is a dry adiabatic lapse rate which is about 1 degree per 100 meter. If I have to kind of plot it, so let's say then this is stable zone. So that is, let's say, some kind of a 5,000 meter. This is something neutral. Okay. This is unstable because let's say like this. There is a sun. At this location, this could be 10 degrees C. this is what happens. Let's say 40 C. This is what is, let's say 0 degree C. So this is my atmospheric lapse, which is typically 1 degree C per 100 meter. So if the ambient air gets cooler, slowed down 1 degree per meter, it means that the atmosphere is stable. If it gets cooler faster, it is unstable. Atmospheric lapse plays an important role. So the standard atmospheric lapse, which is 0.66 degree C per 100 meter. So this is correspond to a stable stratification. Even more stable is an inversion. So generally, wind shear is stronger for stable condition. Less mixing between layer occurs. So thus you have less momentum is transferred at strong winds. Mixing leads to neutral conditions. So obviously the atmospheric lapse rate equals atmospheric these things. What we can look at is that statistics of wind. So at a given site, wind speed and direction. So that means the speed and direction is a function of time. So if only speed is regarded, one can plot time series data. Let's say we can plot like that. This is time, and this is, let's say, one location anemometer. So this can vary like that. So this is essentially one can think about that, let's say, hourly average over 1 year. It's just a sample data. So once you can find out the mean and also the variance with the hourly average within speed over the year. Okay. So what you can have, let's say, varying wind speed, and you can have, let's say, 0 to 4, 6, 8, and so on. So, I mean, you can have some kind of a curve like that with all this data. So this is frequency. This is probability of U. This is wind speed meter per second. This is called the some kind of a histogram. So different distribution can be used to describe this PU, which is probability density probability density function of wind speeds. That is the PDFs. And we can compute a Q, which is the cumulative distribution function, which is CDF. So these are some kind of a statistical characterizations of the distribution, which comes from, again, statistical mechanics, but this is used in turbulence as well. So the property that it satisfied, Q of du use 1. Okay. And one can write Fu is 0 to u, uu, du. So that means I can have P of u is f of u prime. So that is the relationship that one can have between this probability distribution function with the cumulative distribution function. So we can have some example of different distribution function. So the simple one could be Gaussian or normal distribution. So which can be like this. I can have u, which is goes like that. This is u bar, then this is u bar plus sigma u square. This is probability of u. So this is a simple Gaussian distribution or normal distribution, and the distribution function is well known, which one can write 2 pi sigma u square into exponential minus u bar square by 2 sigma u square. Okay. So that's the distribution function for Gaussian distribution that you have. Similarly, another distribution which we have already talked about, that is so this distribution, we talked about is that Webel distributions. That is another kind of distribution function which we'll look at it. How the So these distributions are primarily coming because, as we have seen, that the wind speed is varying with time. As I've been emphasizing that the variation is over the month, hour, week, they are varying. Then you try to make a distribution of that particular. But again, this is very, very specific to a particular location where you would like to estimate that. And then the distribution function, which is very critical in getting the wind power calculated, because we have already seen these distribution functions are definitely advantageous in getting power calculations compared to the power calculation based on average wind speed. Okay, we'll stop here and we'll continue this distribution discussion in follow-up session. Thank you.